Hello everyone. I am going to finish the lecture that should have happened today and didn't because we were talking about gravity so much. Okay, we were last time talking about angular momentum. Okay, and we know that the angular momentum for something is conserved, so the final is equal to the initial only if, so this is a statement that really means delta L equals 0, and delta L equals 0 is very similar to delta P equals 0. So what does that mean? That means delta P equals RF times T. So if we have a force, and that force is times time, that's going to be our change in linear momentum. Well, the same thing happens. Delta L equals our torque times time. And if that torque, which is equal to I alpha times time, if that alpha is equal to 0, then of course I can't be 0. So alpha is equal to 0, that means that the torque is equal to 0, so that whole thing equals 0. So if there is no external torque, then we get a conservation delta L equals 0, which means that the final is equal to the initial. Okay, so important, good stuff, and we're gonna use this bit right here. We're gonna use that, and we're gonna continue on. Here we go. We're gonna look at a lazy Susan. You guys all know what a lazy Susan is? It's that thing on your table or in your fridge or whatever that you can stick your condiments on and your salt and pepper. So, oh God, I don't want to draw any salt or pepper or anything. So all I'm going to do is I'm going to draw a radius. Here's our lazy Susan that's going to spin around. We're going to apply a force to it. That's the force of the person on the lazy Susan. Okay, we're making sure that that force is being applied perpendicularly so that our torque, which is normally equal to a force times the radius times the cosine, sine, sorry. It's the sine of the angle between them. That sine of 90 degrees is 1. So we can just say that it's the force times that radius. Okay, great. So that's our torque. Now, the question is, what is the final angular momentum, LF, if it starts from rest? So LF if omega naught equals 0. Okay. We're going to be taking our time equal to 0.15 seconds. our force applied by the person is equal to 2.5 newtons. And our radius is equal to 0.26 meters. Okay, that's about the right size for a Lazy Susan. And we're going to solve for LF. And LF, we've already done it before. Let's see, how do we want to do this? I'm going to erase that. Okay. We're going to say delta L equals our torque net times T, and that equals L final minus L initial. And L final minus L initial, since this is equal to 0, that gives us our torque net times time. Well, we already know that the torque is equal to this, so L final is equal to our torque times the time. And that's easy to figure out, 2.5 newtons times 0.26 meters times 0.15 seconds. LF is equal to, okay, I'm getting my calculator out. 2.5, enter. 0.26 times 0.15 times. And that is 9.75 times 10 to the minus 2. And that's a kilogram meter squared per second. Kilogram, I'm just checking my units. Making sure that that's right. And it is. So, great. We're moving forward. That is our answer for the Lazy Susan. And we're going to now ask, we're going to say B. What if MLS, the mass of the Lazy Susan, is equal to 4.0 kilograms? It's a heavy Lazy Susan. And I, our moment of inertia, is the same as a disk. So it's equal to 1/2 our mass of the Lazy Susan times the radius squared. So that's our I of the Lazy Susan. And we're going to say L final, L final is equal to our I of the Lazy Susan times omega final. So what is omega final? What is omega final? So we'll solve that. Omega final is equal to our L final that we found, and we're going to divide by our ILS, and that's going to give us this that is going to give us a really cool thing, this really great number. Let's plug it all in. 9.75 times 10 to the minus 2 kilogram meters squared per second. And we're going to divide that by this guy right here. We didn't figure out what that was. Turns out it is 1/2 of 4.0 is 2.0. So we'll have 2 times the radius squared, which is 2 times 0.26 meters squared. And that equals 1.35 times 10 to the minus 1 kilogram meters squared. So we'll put that down here, 1.35 times 10 to the minus 1 kilogram meters squared. And if you notice, this and this cancel, leaving us with the ghost of radians over seconds. Awesome. And let's do a little division. 1.35. 0.135 divide. That is 7.135. 10 divide 0.722 radians per second. So, what did we do? We applied a force. Oh boy, get a hold of yourself. We applied a force like this to a Lazy Susan, radius r. A person did it for a certain amount of time, and we were able to get that Lazy Susan up to this. Now, conservation of angular momentum did not happen. Why is delta L not equal to 0? It's because we supplied a torque in the form of a force of the person times the radius. So that did not equal 0. So we did not show conservation of angular momentum here. But we are going to show conservation of angular momentum now. So let's forget all about our Lazy Susan for a second. And we have to have alpha equal to 0, which implies I alpha equals torque equals 0, because that's 0. So now our delta L is equal to 0. Because the torque is equal to 0, and it doesn't equal, this torque has to be multiplied by time before it can equal this delta L. So the fact that there is no torque gives us this. Okay. Great, we've got that. Delta L is equal to 0. All right. we can say conservation of angular momentum is conserved. So here is where we get to the homework problem that you guys are doing on the test. Not on the test. In homework number 12, it's problem 6. And I changed it. I changed it to be a lot closer to the textbook as example 10.1.5. So in the textbook, you want to look at this example, and that's the problem that we're going to do. And I'm going to do it right now. This thing works pretty well. I'm pretty impressed with this thing. Okay. All I need now is some music. Okay. In the book, and just like the picture on the screen, we have this thing that is coming in and hitting a stick of length L, and the axis of rotation is about one end of the stick. And in the question, in problem 6, they say this is a very thin stick, so the radius that it's going to hit, this ball or puck, is going to hit right here at this radius. That distance, r, is very small compared to L. Not very small, but L is equal to 1.2 meters and r is equal to 0.1 meters. So it's 1/12 of it. We have a mass of the puck equal to 0.05 kilograms. We have a mass of the stick, and that was equal to 2 kilograms. We did the length, we did that. We have the initial velocity, the incoming velocity of our puck. That velocity was equal to 30 meters per second. The center of mass, it's a uniform stick. So the center of mass is right there for the stick, which is exactly L over 2. If that's L over 2, then the bottom side is L over 2 as well. And we want to know, the first thing is, what is the angular velocity, final, okay, after this collision happens. So that little ball or puck or whatever, right before it hits, has this V naught. So it's just like the slightest fraction of a second before it hits. That's the situation. We have an initial P naught. This is the linear. P naught is equal to the mass of the puck times the velocity incoming. Okay, great. But what is our L? Well, that would be the mass of the puck times the radius squared times our omega initial. And what do we know about omega initial? I'm going to write right here, omega equals V over R. So we can come down here and say mass of the puck times the radius squared times our velocity initial over R means we've got mass of the puck times the radius times our velocity initial. And we're going to hold that to the side as reference. Okay, so we'll keep that in mind. Let's move it down a little bit. All right. So what is omega final? We can start with our the fact that there's no additional torques. So delta L equals 0 means L final equals L initial. I'm going to rewrite that in terms of I final, omega final equals I initial, omega initial. And solving omega final equals I initial, omega initial over I final. The light was in my eyes. Okay. But we already found this right there. So let's write out omega final equals MPRVO over I final. Now we just have to figure out what I final is. So what do you think I final is going to be? The moments of inertia add up just like masses add up. So our I total in the end is going to be the moment of inertia for the puck plus the moment of inertia for the stick. The moment of inertia for the puck is easy. We already have seen that before. Right up here, we've got mp(r squared. So moment of inertia for the puck is mp times its radius squared away from the axis. Great. But the stick, that's different. So for a stick, where should I do this? Let's do it over here. I stick is equal to 1/3. I'm using the table that has all the moments of inertia on it. And that's 1/3 mass of the stick times the length of the stick squared. Good. So we'll write over here 1/3 mass of stick times the length of stick squared. And that's our, I'm just going to write it as IF. And that is gold right there. A little box around it. So we're going to say omega final is equal to MPRV naught over MPR squared plus 1/3 mass stick times L squared. Lots of numbers in that one. All kinds of ugly numbers. All the stuff, we gotta plug it all in. I'm not gonna do it. Okay, I'll write it out. You talked me into it. How did I get rid of? I did not get rid of it. 0.1 meters, 30 meters per second. 0.05. I'm not going to put units down here. I don't have enough room, I'm sure. 0.1 squared plus 2/3. 2 is the mass of the stick, 3 is the 1/3. So mass of stick divided by is 2/3, and then our length of the stick is 1.2 meters squared. Okay. Let's plug that all together. Normally I'd have you guys do this. Making me work. Okay. Can do. 30 times 0.05, enter. 0.1 squared times 2, enter. 3 divide. 1.2 squared times plus, and then divide. 0.156, 0.156 radians per second. I believe that is correct. I'm pretty sure that's right. Yeah, I'm almost 100% sure that that is correct. So let's erase a little bit of these things and we'll move up. Okay, so that was the question. A. So let's do that. That was A. All right, B. Now here's B. I wrote you guys a note in the, what they really want is the final. They say they want the initial, but they don't. They just want the final kinetic energy. So what is that final kinetic energy? Well, kinetic energy in rotational sense is 1/2 your moment of inertia times your angular velocity. And if we're dealing with the final, we're dealing with the final of both of those. So we have to use what we have up here for the final of both of those. What's convenient is, if you look right here, that's our I final. So we can take that and use that as a number. But here's the thing. Omega was a part of I final. I don't know if we want to do that or not. There's a bunch of ways you could do this mathematically, but I guess we've already got it. So we'll 1/2. You want to see the math on this? Let's do it. Let's do this. Here we go. We have I final, and I'm taking this equation right up here. Let's star it. That guy. I'm going to square it. So MPRV0 squared divided by I final squared. Well, one of these cancels that one, and we're left with 1/2 MPRV0 squared over 1 I final. But if you look carefully, omega final is that. It's this, one of those, over I final. So omega f, believe it or not, is one of those. So we say 1/2 omega final, and then we are left with MPRVO. I hope you guys followed that. That's one of them. That's this. And together they make one of these. So that's this. Then there's that left over in 1/2. So blah, blah, blah. I think you get it. All we have to do is do 1/2 times 0.156. And did we ever figure out what MPRVO was? Let's look. MPRVO, well, we never really did. So let's do MPRVO. Oh boy. MPRVO is equal to 0.05 times 0.1 times 30. That's 1.5 times 0.1, which would mean 0.15. So times 0.15. And let's let her rip. Come on, computer. 0.15 times 2 divide 1.17. 1.17 times 10 to the minus 2 joules. Okay, and that's B. Alrighty then. We've now done B. Let's move up a little bit here. And we'll erase these little guys. Okay, so then, what is the total linear momentum? So C. What is, now they say what is the total linear momentum before and after the collision in the problem, but they don't really mean that. What they mean is, what is the total momentum finally? So we're going to say that is P final. Okay. How do we go about getting P final? Well, V equals R omega. And if we stick a final on those, that'll be wonderful. Then P final is equal to the mass of the puck times V final plus the mass of the center of mass of the stick. So mass of stick at its center of mass times its velocity at its center of mass. Okay. For the stick, because it's going to be a little different than for the puck, because the radius changes. So let's draw a picture. So here's our stick. Here's the center of mass of the stick. Here's L over 2. That's the distance from the axis to the center of mass. Of course, this R for the puck, that's our R. The puck is hitting here. Is still the same. So for the puck, we have 0.1 times our omega final. And for, that's the velocity puck final. And then for our stick, so let's put that in, 0.5 times 0.1. And we're going to add mass of the stick, which is 2.0, and V final for the stick. Okay, V final for the stick is L over 2. L over 2 is 0.6 meters, and then we're going to multiply that by omega F. So 2 times 0.6 meters times omega F. So omega F gets distributed through, right? It's going to be multiplied by this term and this term, both. All right, that's our P final. We already know what omega F is. Let's go back up here. Omega F. We'll stick a star on that one. Right here. That is omega F. We'll go back down. And we'll finish it off with a flurry. 0.005 plus 2 times 6.6 is 1.2. And we're going to multiply both of those by 0.156. So our final, here I go, I'm going to do a little mathematics. 0.005, enter, 1.2 times, oh man, not times, it's adding, 1.2 plus, and then now we're going to multiply with 0.156. And that equals 0.188 kilogram meters per second. And that is the answer to C. And I think if you go through and look at that example, so I'm going to reiterate, look at example 10, where is it? Where did I write that? 10.15, and the figure in the book is 10.12. Oh, I'm sorry, yes. The moment of inertia figure is 10.12. That's where all the moment of inertias are. So, thank you. I hope that helps everyone and get their homework done. Plus, you needed to see this. And from now on, we will be moving on to other things. Congratulations.